Alright, so I thought we'd go ahead and work through an example. Now, in terms of the software I'm using for this is a software program called SMath. If you're curious, you can find this online. It's a freeware program. You can download it for free. It's very similar to, basically it's very similar to MathCAD if you used that before. It's sort of a freeware version of MathCAD. And if you're curious, you can also find some videos on my YouTube channel documenting how to use SMath. Anyway, I want to work through this example here. So this is going to be probably the simplest type of reinforced concrete beam analysis you can do. We have a single layer of reinforcement. We know all the dimensions. We know all the material properties. And I just want to calculate the design moment capacity. And this would include both the nominal moment capacity and the resistance factor. So to get combine those together to give us the full moment capacity. Okay, so we have 3,500 psi concrete, so that's what all of the concrete is. We have concrete with a cover depth at the bottom of 3 inches. And we haven't talked about cover depth requirements yet, but we will at some point. And then we have a overall beam height of 18 inches and a beam width of 12 inches. Okay, so I'm going to use the steps that we discussed in class. And in fact, I'll go ahead and write them out in this as I work through this. So, one, let's go ahead and assume the steel has yielded. Assuming the steel has yielded, calculate the tensile force, the total tensile force, the total tension force in the steel. Okay, and actually before I do that, I might just go ahead and define some basic quantities. So, first of all, I might say my area of steel. And you can, of course, do this by hand, but I'm just doing it in SMath because I'm creating some calculations that will be useful later on. Area of steel. And this is going to be AS equals. Now, this table here, this is just a reference table I found. You can find these in many places. This is just a table showing the nominal area and the nominal diameter of various rebar sizes. So we have 3 number 10 bars. So, and each number 10 bar has a nominal area of 1.27 square inches. So I'm going to go ahead and do that. So that's 3 times 1.27. And I'm going to put units here, inches squared. And the nice thing about programs like MathCAD and SMath is that they speak units, and so they'll handle certain unit conversions. Although we do have to be very careful with them when doing empirical calculations that have units sort of built into them. And we'll look at that as we go along. So we have an area of steel. Then we have some, let's see, so we have our area of steel. Now we just need to get some properties. Let's get the material properties. Actually, before we get the material properties, let's define the other geometric properties. So beam height. Beam height, H is going to be 18 inches in this case. And our beam width is going to be 12 inches. And I'll try to be consistent with the labels, the variable labels in the book and what we've used in class. So beam width is 12 inches. And then I'll go ahead and just say the cover depth. And there are different variables for this in book and code, but I'll just go ahead and say DC for a depth of cover, or maybe just like a thickness, maybe like a T sub C, a covered thickness, 3 inches. Okay, so in terms of definition of cover depth, the cover depth is the distance. If you zoom in really close here, you can see that this 3-inch depth does not go to the center of our steel here. Instead, this 3-inch distance goes only to the outer surface of the steel. However, when doing our calculations with beam depth D, we need to have the distance from the top of the beam to the center of the steel, the centroid of the steel. Okay, so let's say beam diameter, or just a bar diameter. Our bar diameter is going to be, again, these are number 10 bars, and so they have a nominal diameter of 1.27 inches. So I will say that dB equals 1.27 inches. Again, total area, oh, and I should probably go ahead and calculate this. That is equal to, well, I don't want it in meters squared, so I'll go ahead and do this in square inches. Okay, so we have a total area of 3.81 inches squared and a bar diameter of 1.27. Now, consider this carefully. If I want to get the actual depth of the reinforcing steel, here's how I'll calculate this, for this case anyway. If I had 2 rows, it'd be a little bit more complicated, but not too bad. So if I want to know the depth of tension steel centroid, or simply D, well, this is going to be the whole height of the beam, H, minus this cover depth, so that's minus dB, or minus TC, minus half of the bar diameter. Because again, I want to get the distance from the outer surface of this beam, outer surface of the top of the beam, to the centroid of my line of reinforcing here. So I'm going to do not dB, but dB over 2. And that produces a depth of 14.365 inches. Again, that is the height, the overall height of the beam. I'm looking for the distance from here to the centroid here. And so I can get that just by subtracting from H, 18, you know, from my, if I start with my height, which is H, which is 18 inches, I subtract from that my cover depth, and then I subtract from that half the bar diameter. That will give me my distance D to my centroid. Okay, and I think that should do it for geometric properties. And then we also have material properties. In fact, I might just go ahead, if I want to be really nice, I could go ahead and label these. I put a little header on this, so section properties, and then material properties. So I'm going to have the yield stress of my steel, yield stress, and that would just be Fy, and that's going to be, this is provided I have a yield stress of 60 KSI, kilopounds per square inch, or KSI, and I'm going to define that as such. And then I have my concrete 28-day compressive stress. And that's F prime C. Now, F prime C is equal to, and I'm going to say this is equal to 3,500 PSI. I'm just making sure that this is recorded correctly. Okay, good. Okay, so I now have all of my, so programmed into SPath, I now have defined all of my material and section properties. Let's see, what else might we need? We probably need to calculate, we should have our assumed concrete, well, assumed in the sense that it is a value we're assuming, but this is actually dictated by the ACI code. And so I'll say concrete compressive strain, or more specifically, concrete crushing strain. And this is our epsilon C ultimate. Epsilon C ultimate, and this is going to be 0.003. Okay, so we have that. Looking at this, if there's anything else we need, anything that can't be calculated. So I think that'll do it. Okay, so we're going to have a lot of other things to calculate, but everything else should just be able to be calculated. Okay, so first thing we're going to do is assume the steel has yielded and calculate the total tension force in the steel. Well, if the total, as we've discussed, if all of the tension steel has yielded, in other words, if we are at a strain much greater, if the tension steel is at a strain much greater than its yield stress, then, or much greater than its yield strain, then we'll have a full yield stress developing across all of the area of our rebar. Oh, also I might just go ahead and also one other thing. I probably want my, I keep thinking of things I want to include on this. Another thing I might want to have is my steel elastic modulus, or Young's modulus. And I'll just define this as ES equals 29,000 KSI. And I can go ahead and calculate my yield strain, my steel yield strain. And this would be epsilon S, or actually epsilon Y, maybe for epsilon yield. Epsilon Y is going to be, that would be just Fy, or actually, yes, Fy divided by, you said S, or 60 KSI divided by 29,000 KSI, or 0.00207. So basically, again, when we're assuming the steel is yielding, we are assuming that the strain of the steel is greater than the yield strain. We don't know this initially, but it is a reasonable assumption if we're assuming a tension-controlled section. And so we're going to assume this, and we're going to run through the calculation to determine the moment capacity, but then we'll always have to go back and verify that we are within the yields, that we are beyond the yield strain of the steel. So if we assume the steel has yielded, our tension force, well, again, if all the steel has yielded, then our full tension force can be directly calculated just by multiplying the area of the steel times the yield stress of the steel. So that would be A sub S times F sub Y, and that would come to that in newtons, or as I prefer, kips. I'll be doing this in kips. So in other words, if we have as long as the steel is fully yielded, we will have a tension force of 228.6 kips, approximately. Nominal, of course, not without any kind of resistance factor built in. And what does this represent? Well, again, this represents the maximum tension force that can ever be developed within our steel rebar. Again, said another way, this represents the maximum tension force that can be carried by our rebar. We're assuming it is yielded. And at its maximum, essentially at its maximum capacity. And so we then will simply assume this and then calculate, we will assume in turn that there is enough concrete that can be mobilized to balance this force. In other words, in order for this to be true, we have to have enough concrete depth in our concrete, that there can be but when you apply 0.85 F prime C over that depth, over the area of that compression block, we're assuming that there's going to be enough of that there in order to balance. There's going to be enough concrete available in order to balance this force here. So if not, then we'll have to do a more complex analysis. But for now, we're just going to go ahead and assume the steel is yielded, and then we'll calculate our depth of our compression block, etc. Okay. So the next thing I want to do is calculate the depth of our compression block. And let's see, let's go ahead and do that. So next, calculate depth of compression block, A. Now, the first thing we're going to have to do is determine our beta 1 value. Our beta 1 value, the ratio between, Actually, before I do, I suppose I don't even need to do that before I calculate A. So let's go ahead and calculate A just based on equilibrium. Again, as we've seen, the total compression force must be equal to the total tension force if this is to remain in equilibrium. So we can simply divide we can calculate A directly just by multiplying just by saying, okay, this is ASFY divided by the width of the beam times 0.85 F prime C. Okay, so A is simply going to be, this is going to be B, the width of our beam, times 0.85 times F prime C. There. And all of that divided by, oh, actually I have that backwards, sorry about that. Area of steel times Fy, or I could just say, you know what, I'll just go ahead and say this is equal to the tension force divided by B times 0.85 F prime C. Or another way of thinking about this is, if I want to break, I could break this up further and say the total area of mobilized concrete of concrete compression block. And this is a bit of an extra step that I'm just including to illustrate where these equations are coming from a bit better. And so what I could say is, I could say, okay, maybe something like AC, I don't know, ACC, area of concrete compression, that is simply going to be equal to T divided by 0.85 times F prime C. Or, in other words, this is going to be equal to that many meters squared, or what I will use is inches squared. And that's way too many decimal places. Okay, so in other words, in order to balance, with a total tension force of 229 kips, if I limit myself to that 0.85 F prime C value, 0.85 F prime C is 0.85 times my F prime C of 35, so again, of 3,500 PSI. So again, I have this compression block, and that compression block represents a uniform stress of 0.85 F prime C applied over a certain area. And the area of that block has to be equal to 76.844 inches squared. Or I could calculate the depth of the compression block just by dividing by the beam width. But once I have the area, it's just a matter of dividing by the beam width. Depth of compression block. So that would be A equals ACC divided by beam width B. So that would come to 6.4 inches about. Maybe put 3 there for completion. Okay. Or another way I could say this, I could just calculate this directly without the intervening area calculation. And we should get the same number. So I could use this T divided by B over 0.85 F prime C, or I could even eliminate this middle step and just say this is equal to area of steel times the yield stress of steel divided by B times 0.85 F prime C, and that will come to this, that should come to the same value in inches. And that's not surprising. This is just, again, this is combining them together in this calculation on the bottom row here. This is combining them together into a direct single calculation. These three here are more just breaking it down into a series of steps that make it a little bit easier to visualize the velocity here. Okay, so now that we have that, let's go ahead and get, I want to go ahead and, so now we know basically the depth of the compression block, and now I want to verify my assumption that the steel has yielded. So 3, verify that steel has yielded. Now, in order to do that, I need to go, I need to determine the depth C of the neutral axis. So we actually go ahead and write that out. In order to verify that the strain of the steel exceeds the yield stress of the steel, I need to calculate C. the neutral axis depth C. Then, in order to do that, I need to get the beta 1 value. The beta 1 value. So, beta 1. This is our ratio of compression block depth to neutral axis depth. Our beta, or more specifically, our beta 1. And this is the reference again for this is, let's see, this is, that was 22.2.2.4.3. ACI 22.2, 0.2.4.3 here. And so beta 1, now in our case we have a, okay, so our F prime C again is equal to, in PSI, 3,500 PSI. So therefore, because our beta 1, because our F prime C is below that 4,000 PSI cutoff, our beta value is going to be 0.85 in this case. In other words, I could say this is, if I wanted to label this a little better, I could do this here. So I could say this is less than 4,000 PSI. Less than 4,000 PSI. Therefore, based on the provisions of 22.2.2.4.3, my beta 1 value will simply be equal to 0.85. Okay. Now, I know that I have the relationship between strain and stress, and okay, so I know something like this. From the notes in the previous lecture, we had something like this, where 0.003 over C equals epsilon S is equal to epsilon S over D minus C. And that's fine, but what I really want to do is I want to I want to directly calculate C using this, and that's always a little bit trickier. So how might we do this? Well, we need, so again, well, actually, let me think about this. Calculating C is actually going to be fairly straightforward now that I think about it. Since we already have A, and so we can go ahead and calculate our neutral axis depth. That's C. C then is just going to be equal to A divided by beta 1. Oh, not B1, sorry, that should be beta 1. And that in meters, or 7.53 inches. So C is 7.53 inches. Again, that is our neutral axis depth. Now we need to calculate the strain in the steel. And if you work through the similar triangles, you will find the following relationship. Strain in steel. If you look at that 0.003 over C equals epsilon S over D minus C, you can calculate the strain in the steel fairly easily by just saying, okay, epsilon S is equal to epsilon C ultimate, our ultimate compression strain in our concrete, or crushing strain in our concrete, divided by C, and then times D minus C. And that in turn comes to 0.00272. All right, so there is that. Okay. So let's go ahead and, so we now have the actual strain in the steel. In other words, if our steel does in fact, we are assuming in this analysis that the steel yields, and if it does, it will have a strain past the yield strain. So let's actually determine, let's compare those. let's directly compare those strain values. So our yield strain, again, for the steel, is 0.00207, and in fact, this is indeed less than epsilon s is equal to 0.0027. So in other words, our strain, our calculated strain, does in fact exceed the yield strain. Therefore, the assumption we made is true. The assumption we made is true. The steel has yielded before the concrete crushes. So that indeed does work. Our assumption is true. Again, this equilibrium analysis is assuming that we have full yield stress in all of our rebar, all of our tension reinforcement, our steel tension reinforcement, and that is only true if the steel reaches its yield strain before the concrete reaches its crushing strain. And so that should hold true in most cases, but not necessarily always. But we do need to go ahead. So it is a reasonable assumption to make, but it is just something we do need to verify. Okay, so there's that. Now, so I can go ahead and say our assumption is valid. The steel has yielded before the concrete crushes. Okay, so we have validated our core assumption. Then 4, I want to go ahead and compute the nominal moment capacity. So compute the nominal moment capacity. To do this, well, okay, so I have, again, a moment is created by a couple, or two equal and opposite forces separated by a certain distance. And since we already have the force to calculate the moment, we just need to calculate the distance between those two forces. And so that moment arm, that's the moment arm, and the moment arm, which we use the variable JD, JD again is going to, if we consider the dimensions, it's going to be from the centroid of the compression block down to the depth here of the centroid of the steel reinforcement. So that is simply, as we discussed in class, this is just D minus A over 2. Or in this case, we would have a moment arm length of 11.16 inches. So that's our moment arm length. Now, since we have the moment arm, and we have the value of the force that moment arm is carrying, we can then, or the moment arm that force is acting through, we can go ahead and calculate the nominal moment capacity. And that nominal moment capacity will simply be m sub n. Well, that's just going to be JD times T. And that will then come to, well, it wants to report this in joules, but that's not going to work. So instead, we're going to do kip feet. And I'll go ahead and put just maybe 1 decimal point on that. And so we have a nominal moment capacity of about 213 kip feet. And that makes sense. We have a moment arm length of about 11.16 inches. So approximately a foot. Our tension force is, our total tension force is about 228 kips. So yes, that makes reasonable sense in terms of the right order of magnitude. So that is the nominal moment capacity. And again, what this represents is this is the moment capacity, that the moment that the beam will carry past the point that the steel has yielded, but right at the point where the concrete begins to crush. Okay, so next, let's go ahead and determine our phi, our resistance factor phi. Phi. And phi. And again, this is based off of, let me get the ACI reference there again. that is ACI 21.2.2. ACI 21.2.2. Now, because our, okay, so let's see. We need to figure out if we're in the tension-controlled region or not. So what is the strain in the steel? So our strain in our steel, epsilon s, is equal to 0.0027. Now, it's definitely greater than the yield strain, which is 0.00207, but we still might end up in that transition region between the tension and the compression controlled. If we're below the yield strain of the steel, we're in the compression controlled, but we still might end up in that boundary region. So let's go ahead and calculate that. So is this less than, so we need to find the relationship between epsilon yield plus 0.003. 0.003, and that's 0.005. So that's not actually good. We are not actually within the tension control. We're not actually within the full tension controlled region. So we're not going to be allowed to use the full. We're not going to be allowed to use the full phi of 0.9. We're actually in the transition region rather than the tension controlled region. Okay, so we are actually in the transition rather than the tension controlled region. Let's just double check that because we have 60 KSI divided by 29,000. So our yield is that. Yep, that makes sense. And epsilon s d minus c. Yep, that does seem to make sense. Okay. So d minus c over c. Yes, and I believe that should make sense. Yeah. Okay. Just double checking some of my math. And so our epsilon s is then in this transition region between these two. It's between this and the yield strain equals that. So we're actually in this weird transition region where we're not compression controlled, but we're also not, we don't actually have enough of a margin yet to consider ourselves full tension controlled. So we're not going to, so we have to take a reduced phi factor. Now to do this, we have a couple ways of doing this. So our phi factor here, we will have to calculate the, okay, so the phi factor equation is based off an interpolation between the two values. So phi factor in transition region. So let me actually pull up Paint here. I think that might help. So I'm going to do make this a little bigger. I want to create a graphic to illustrate what I'm going to do. Because I know this can be difficult to follow sometimes. So again, from before, for our phi values, so if we have phi on this axis and strain on this axis, well, tension steel strain. On this axis, we have this kind of trilinear relationship where we start up like this, then we move over, then we are constant again. So here we are at 0.65. Here we're at 0.9. And then in terms of the strain value, the corresponding strain values, here we have the yield strain. I'll just use an EY instead of an epsilon Y because this is Paint, not S math. And then EY plus 0.003. So what we found in this case was that we are actually, we're going to be right we're somewhere around like right here. So we need to find the equation of this line or do some sort of interpolation in order to actually find that strain value. So I'll go ahead and put this little graphic, this wonderfully high-tech, high-precision graphic over in this SMath page again. And so the strain in our steel, the strain in our steel is this 0.0027. Now we could do this a couple ways. You can use similar triangles. You can do it however you wish. But using a simple method, I could just say that my phi factor, again, this is simply interpolation. You have one known point here. You have another known point here. And so our phi factor would just equal something like this. We would have a phi factor. Again, because we are in the transition region, we have to do this linear interpolation. Our phi factor would be 0.65 plus the total change between EY and epsilon y plus 0.003. So that would be 0.35. No, 25. Basically, this is a slope of a line, 0.25 over, well, epsilon yield to epsilon, the total horizontal distance here would just be 0.003. And then our, so we're going to start at 0.65, and then depending on the ratio, or how far along we are here, we'll increase by that. We'll increase by we'll have a slope of 0.25 over 0.003. Does that make sense? Let me think about that. Yes. Actually, I should probably, I think I like it a little bit better if it's 0.25 times the ratio of a particular point along the total distance. So like 0.25 times, let's say, because this is our total increase from here to here, and then we want to look at the ratio of the difference between epsilon s and epsilon yield over the total horizontal length. So that would be epsilon s minus epsilon y divided by 0.003. And I think that should do it, because yeah, that will give you the fraction of this triangle. This will give you the fraction of the horizontal distance that you are along here. And then, yeah, and that will give you the fraction of the horizontal distance. Then you'll add that fraction, you'll multiply that fraction times the total increase between the two end values, and that should give you the final phi value. And so here we would, for this, we would have a phi value of 0.704. Now, there are many ways to do this. In fact, I would actually do this a little bit more elegantly if I was doing hand calculations, but it's a little easier to demonstrate with similar triangles. This is just interpolation, but there's many ways you could set this up. You could even set up a, two known points, actually derive the equation of the linear equation in that gap, in that transition region, but you could also use this interpolation type method. Use what I would just encourage you to, however you figure it out yourself, find some way of making sense of calculating the transition region, the phi factor in the transition region, and then work through the calculation to confirm for yourself. Because the thing about this kind of interpolation is there's many different ways to do it, and you just have to find a way that makes sense in your head. So, okay. So we now have our resistance factor. Now we just need to go and determine our design moment capacity. Calculate our design moment capacity. And this is going to be fairly straightforward. It's going to be the multiple of phi times mn. So that's going to be phi times m sub n. Or it wants to give us something in joules again, but no, we're going to tell it I want this in kip feet. And so something like this. Oh, that's still way too many decimal places, maybe just one. And I'll go ahead and put a box around that because that is our final answer. Not the nominal, but the design moment capacity of this section would be 149.8 kip feet. So again, we've calculated, the method we used here was we calculated our tension force, assuming that the steel had yielded. Based upon that, we calculated the depth of the Whitney stress block necessary to produce equilibrium. Then we verified our assumption that the steel has yielded based on actually calculating the strain present within the steel, and we found that that was indeed greater than the yield strain in the steel. Then we went ahead and calculated the nominal moment capacity. We calculated a phi factor based on what region we were in, the tension controlled over here, the compression controlled here, or the transition region. We found we were in the transition region because the strain in our steel is between the yield strain and the yield strain plus 0.003, so we're in that transition region. So we had to use interpolation to calculate the actual phi factor. And finally, we calculated the design moment capacity. Now, the only other thing I want to do is verify that minimum strain or minimum reinforcing steel is present. That minimum reinforcing steel is present. And again, this is based on ACI 9.6.12 or 9.6.1.2. 9.6.1.2 as follows. Now, okay, so on this, let's go ahead and do this. Now, for this calculation, I'm going to have to like cancel out the units because these are empirical calculations, and so if I go ahead and just put in like, for example, AS min, I'll go ahead and calculate 1 and 2. I'll define maybe like a 1. The first value, that is that 3 times the square root of f prime c. The square root of f prime c divided by fy divided by fy times bwd. That's not right. There we go. Hopefully that's working a little better. Times BW. Oh. No, I don't want that. Okay, there we go. Can be a little persnickety sometimes. Now, if I just do this, I'm going to have a problem. And the problem with that is that I have it can see that there's something, oh, actually, first of all, there's not a BW, I just have a B here. But I have all sorts of problems, and the problem with this is that I end up with these weird fractional units because SMath, like MathCAD and other similar programs, it speaks units. And that's fine if you're doing just straight physics calculations, like straight calculation, first principles calculations based on, say, multiplying stress times area to get a force. It can convert the units as needed. That's fine. But this here is an empirical equation, and that produces some difficulty. And the reason for that is that the reason it produces difficulty is that you have an equation that is built around that is derived or empirically derived, experimentally derived around certain units. And so this equation is assuming that you're putting in a number for f prime c in psi. So that's not going to work. So instead, what I need to do is I need to go and strip the units out. And here, I'm going to divide by psi in order to strip the units out. And I still have one slight problem here, and that is that this that I still have this fy, which is in ksi. So what I should do is I should go and divide out the ksi. However, what's interesting here is that, okay, so this is in ksi, but to actually make this equation work, I probably want to put this into psi to make sure that way I can just divide out the equations fairly easily. That won't change any of my other results because SMath will handle the unit conversions until it gets down to something like this, where I have an empirical equation. So again, I need to divide out the units, and I'm going to use psi because I just redefine that as psi. If you're using a program like this, I would encourage you to just put your stresses all in psi and then strip them when doing any kind of empirical calculation, such as this one. And so we get a value 1 equal to that many inches squared. And again, this is all of the reason I applied them only to this rather than these is that this is meant to be a fraction of your areas. So this is meant to, everything in the parentheses here should come to a dimensionless quantity that is just multiplied by b times d. And so I can leave my inches in there and that will be fine. But anything with a root, anything where you're just dividing by a stress, that's probably good where you'd want to strip the units out. So this is our first limiting value, minimum area value, and our other one, which I'll just go ahead and call AS-min2, is 200 divided by the yield stress, which again I want to strip the units out of, times all of this here, times BW, or just B, times D. And that will come to that many square meters, or more useful for us, square inches, or 0.5746 square inches. So what this is saying is that regardless of what your equations tell you need in terms of strength, we are going to require you to have a certain minimum amount of tension reinforcement. And so AS, I can just define an AS min total. That would just be equal to the minimum. I'm going to insert a matrix, so just a simple 2 by 1 array or 1 by 2 array. And so just AS min 1, AS min, and it will just pick the minimum of those two values. Actually, wait, I probably want to make that more of a max. Okay, we want the maximum of the two minimum values, which should then come to, oh, did it not like that? AS min, let's see, what doesn't it like about my AS min 2? Oh, I know the problem. I'm below where I defined it. So that will work. That should work now. And that will be expressed in inches squared. So our minimum area of steel, again, we have to check these two conditions, but then once we check the two of them, we calculate both of them, and we simply take the larger of that of those two. And these are separate limit states based on different aspects of research, and the overall minimum area of steel for tension reinforcement, regardless of what your mass says you need for strength, you are required to have a certain minimum area, and that minimum area is 0.576. And so let's compare that explicitly to our actual area of steel. Our actual area of steel is 3.1 square inches. So yes, we are comfortably over our AS min. That many inches squared. So we have no problem there. Now if we did find we had less steel than that, that would actually be a design problem, because then we'd have to go and redesign the beam. If you found that you're reinforcing steel, you have less reinforcing steel than provisions require, then you would have to go back and the minimum required by ACI, then you would have to go back and actually recalculate, calculate a new area of steel and recalculate your capacity. I'll undo this all over again, which would be a pain in the butt to do by hand, but the nice thing is about a calculation sheet like this is I can change one number. If I want to change this to 19, I can, and everything just cascades through. Although if I wanted to make this truly automatic, I'd have to create some sort of if statement based for this phi and for our beta 1 value. Although we could do that, and maybe I might actually do that in a later example. Okay, so that's a good first example of calculating the yield stress, the design moment capacity of reinforced concrete beams, single reinforced concrete beams. Again, our methodology is we are first assuming the steel is all yielding, and so because of that, all of the steel will be carrying the full yield stress, carrying a stress equal to its full yield stress. So the steel will essentially be totally maxed out and will be carrying all of the stress, all of the force and stresses that we're going to be allowed to carry if we can only go up to the yield stress. So we assume that, then we calculate what depth of concrete is needed to produce equilibrium with that. Then based on that, we calculate a neutral axis depth, do a confirmation of our strains to make sure that the steel has indeed yielded at that assumed value. And then finally, we go and calculate the moment capacity and apply some code checks relating to minimum area reinforcement. Okay, so that was a simple example of reinforced concrete beam analysis. That is about as simple as they come, and hopefully that you realize now why I'm using these computer methods. Because some of our more complex problems, they're going to involve iteration and calculations and things even more complex than this. This is about as simple as it gets in terms of just analysis, let alone design, and things do get much more complicated when looking at things like T-sections. So I'm really a fan of these computer methods. I love SMath. It's something I use a lot. And so it's something I'd encourage you to look at too, this either SMath or MathCAD. MathCAD you may find on the university's IT services, or you may be able to, or you can just find SMath available as a freeware download. You can find that just by a quick Google search. Okay, that'll do it for now. Hopefully you found this video a bit informative. Working through the example, we're just working through a long form example of calculating the design moment capacity of a singly reinforced concrete beam. All right, that'll do it for now. And as always, thank you.